Hi everyone, welcome back again to our YouTube channel, and in this lecture we'll find out FFT of the sine wave or the mixed tone which we had generated in the last lecture. So the very first lecture we talked about generation of sine wave. In the second one we added a noise tone to the sine wave and found out a mixed tone, and then after normalization what we got is normalized tone. Okay, so we are going to find out the FFT of this normalized tone. So we want to find out the FFT of this normalized tone. So to find out the FFT, we need to import the necessary library for it from the Python. So first one is from scipy.fft, import FFT, FFT frequency. So since we need to calculate the FFT, that's why we are importing FFT, and to plot the FFT on the frequencies domain we need the frequency, right? That's why FFT and then FREQ. This will give us the frequency on the x-axis. So to begin with, let's now define a variable which gives us the number of samples on the x-axis. Okay, how many samples do we need? So what we can say, the number of samples in the normalized frequency. So to define that, we know that number of samples, how to find out number of samples would be nothing but the sample rate. So SR we have already defined, multiplied by the time. So you can see this in the definition of the function here. Sample rate into duration gives us the number of samples, right? So how many samples we want is defined by this. Now the next step is to writing the code to plot the FFT, right? So we need a y of f, that is the range of the function, equals FFT. We are finding out the FFT of given signal. So FFT of which signal? The normalized tone, right? This graph basically. So just copy it, the normalized tone from here, which we had already got after adding the noise tone along with pure signal and then doing the normalization over it. So just copy and paste it, this normalized tone here. So this is about the y-axis. Now to plot it we need frequency on the x-axis. So for that let's write xf equals, the first argument is basically the number of samples. Okay, so we'll write it as n, which we have defined it here. Okay, and the second argument is the spacing between the samples. So that is 1 over the sample, 1 divided by SR. So this is about x-axis. Now we need to plot them. So for that, as we know that plt.plot will help us to plot this function, and first x and y, we want to plot x and y. So write down here x of f comma y of f, and at the end we'll write plt.show to show the plot. Let's run the graph now. So what we are getting, the graph, this is not what we were looking for because there is no frequency on the x-axis. This is something which we were not looking for. The reason behind it is the way we plot. So here we have given x of f and y of f, that is real and imaginary part of it, right? A Fourier transform gives us a complex function. Let's say we want to plot a plus iota b. So what we are doing right now, x of as a and y of f as b, but that's not the correct way to plot it. So to plot the y of f, we need to find out square root of a square plus b square, which is a real number, right? Which is not imaginary. So for that we need to use a function called abs, and we need to call np.abs in our code. So if we use this function, we can get the expected graph what we were looking for. So let's write down np.abs here and then y of f. Give it a run once again now. So now you can see we got a plot which contains a frequency on the x-axis and the amplitude on the y-axis. So as we can see, there are 4 tones. So let's analyze the graph for a moment. We can see that there are 2 peaks in the frequencies and the mirror of those peaks in the negative frequencies. So there are 4 peaks. So the first one is at 500 Hertz, that is the signal tone of the sine wave, which we had defined here. Okay, and the another one is at 5000 Hertz frequency. Okay, so that you can see here. The second tone, this one is at 5000 Hertz frequency. So this is the 2 frequency in the positive side and the mirror image of it on the negative side. That is because whenever we give a real valued input to a Fourier transform, we want to find out the Fourier transform of real valued input, we get a positive negative symmetry in FFT spectrum. Now let's say we want to change this frequency of noisy signal. Let's say let's make it 25,000 and see what happens in the frequency spectrum. Give it a run once again. So you can see the noise signal frequency, the peak has been shifted towards 25,000. Okay, so this is the noisy signal what we had given to the mixed tone, and this is the signal at 500 hertz. If you want this to move this signal as well, we can make the changes. Let's make this 500 as 10,000. Give a run once again. Run it. So you can see here now this is 0, and at 10,000 is the signal, the pure tone signal, the sine wave, and at 25,000 we have the shifted, that is basically the noisy signal which we induced in the pure tone signal, which is at 25,000. So this is all about finding out the FFT transform of a given sinusoidal signal along with some noise into it. The next step, let's say we want only the positive side of this spectrum, we don't want the negative side. So for that we can use a function. For that we can make the changes in the graph wherever there is FFT. Let's make rfft. So make here r. So let's add r at the front of each of the FFT. Okay, so put here r and put here r as well. So here I forgot to put r, put it here again. So on adding r in front of every FFT, what we get, so you can see now we're getting the tones only at positive frequency. So at 10,000 and 25,000. So 10,000, the peak at 10,000 is basically the signal which we were looking for, and 25,000 is the noise which we added in the given signal. Okay, so that's all about FFT in general. So thank you for watching the video. Hope you found this video insightful. Stay connected